Hello everyone and welcome to this video. Today I'm going to talk about the most used contact types inside ANSYS Mechanical. Through this video I'm going to explain and show the difference between each one of these contact types, and finally you will get from me some tips and tricks that you can use in your models to improve conversion stability and efficiency at the same time. But before we start, actually in finite element analysis, defining how paths interact with each other is critical. By default, paths inside an assembly do not recognize each other's physical boundaries unless a contact region is specified. Choosing the wrong contact formulation can lead to catastrophic convergence issues, false mathematical penetration, or inaccurate stress results. So as you can see on the screen, I already prepared an experiment on these like 5 double plates, and between these two plates on each model is a contact already defined. These contacts are bonded contact, rough, no separation, frictionless, and frictional contact. On the left side, you can see like the boundary conditions, where they are there like to explain like how each one of these contact types actually work. And to the right, you can see the total deformation like after solving the problem. So let's start first with the bonded contact, which is like already defined on the first model to the top. And you can see on the right that we have like zero deformation on both plates. Actually, bonded contact setting is the most fundamental and default configuration in ANSYS, so it acts as a perfect mathematical weld between the contact and target surfaces. Separation, sliding are not allowed, so purely linear solution. Any initial gaps present in the CAD model are automatically closed mathematically, and initial penetration are ignored. So this is bonded contact. Now, for the rough contact models as specialized state where surfaces can lift off from each other but cannot slide even a fraction of a millimeter if they are touching. So, as you can see on the second model, we can see that we already have nearly like zero deformation, but if I can zoom in to this plate and increase or exaggerate the deformation, you can see that these two plates, they can separate, but they cannot move. And this is actually what's like rough contact. Rough contact allows separation, but doesn't allow sliding. Now, let's go to the no separation contact. The no separation contact was defined here on the third model, and already like an upward force on the top face of this plate already defined, in order to try to get this plate like up. But no separation contact is a specialized setting that prevents parts from pulling apart, but allows them to slide effortlessly against each other. As you can see on the model, I'm gonna give this back to 1, that the plate on the top, even if we are already defined an upward force, the plate is still like sticking to this plate, because no separation, it means it cannot like separate from the defined like faces, but actually it can slide or move. Because here we didn't like define any like a movement in any direction or force, so it seems like it's still on the place, but actually it can slide. Now let's go to the frictionless contact, which is on the fourth model here. In this model, what I did is like I defined like a force with 100 Newton downward, and I tried to move the top plate 5 millimeter on this direction, on the negative Z direction. As you can see on the deformation, the plate here, it's already moved. So in frictionless contact, like represent like a classical unilateral like contact behavior where surfaces can separate freely but cannot penetrate each other. So gaps can form naturally depending on the external loads if the separation occurs. So normal pressure drops immediately to exactly 0. In this case, frictionless, what we gonna or important to see actually is the frictional or reaction force between these two plates. And as you can see, I already defined a downward force of 100 Newton, and you can see that on the like plane XZ that I already almost get like near to zero forces. And this is what's like frictionless mean, where there is no resistance on the plate. So it can move but no resistance. The last contact type, it's a frictional contact. The same like boundary condition was defined on the fifth like model down, but we already defined a frictional contact with a coefficient of 0.12. Now, as you can see, frictional contact actually can separate and it can slide, but it will like face some resistance depending on the frictional coefficient you already like defined. In our case, if we go and see the reaction force, you can see that I already have the reaction force to up like with 100 Newton, but I see that I have around like 19 to 20 Newton as a resistance force on the counter like direction. As you can see, the direction of my reaction force in comparison to the like in which side this top plate it moves actually. And this is actually the frictional contact. So now let's see together a summary like about these 5 contacts. Actually, as you can see on the screen, we already talked about these 5 contact types: the bonded, rough, no separation, frictionless, and frictional. So the difference between these contact types, actually with a bonded contact, it cannot like open or close, it cannot slide, and it's like a linear solution. The rough contact, it can separate, but it cannot slide, and it's actually a nonlinear solution. The no separation contact type, it cannot like separate, but actually it can move and slide as the frictionless contact type do with a frictional coefficient of 0 actually. And this is for sure, it's also a nonlinear solution. The frictionless contact type, it can separate and it can slide with no resistance, where frictional coefficient is actually like 0, and it is like a nonlinear solution. The final contact type, which is the frictional contact type, it can separate and it can slide, but with some resistance, which is like depending on the frictional coefficient that you will define in your model. And this is also a nonlinear solution. Now, I'm gonna to give you some tips and tricks that you can use in your model to improve your conversion stability and efficiency at the same time, which is like very, very important in your simulation workflow. So as you can see on the screen, we have like inside each one of these contacts to define, like we have or we must to define each time like the contact and target surface. So there is a rule actually that it can help like ANSYS to understand like or to converge like better. And this rule actually for the contact and target is as follows. So always specify the smaller body, the more intensely like curved surface, or the softer material as the contact surface, and the larger, flatter or stiffer body as the target surface. ANSYS checks for penetration from contact node into target surfaces. So if you follow this, you will gonna like more efficient like conversions in your model for sure. Second, managing the pinball region. So the pinball region is also like a subsetting inside each one of these contact types, and is a visual like sphere, depending on the value you can give, created around the contact elements. So for nonlinear contact, frictional or frictionless, change the pinball region from program control to a specific radius value if parts have large initial gaps. So if we have like two plates which they are like 10 millimeter like away from each other, so we have to define like an enough like radius or a spherical form that can cover this distance between these two plates in order to let ANSYS like know that where is the target, where is the contact surface. This prevents the solver from missing the contact entirely during structural movement. So if your like pinball is not like big enough, it will be ignored this contact and he will not see the contact and target surfaces. So be careful about this like parameter. The third point, like overcoming no convergence. Like if your nonlinear like simulation fails to converge, adjust the normal stiffness factor down to 0.1 or 0.01. Like depending on my experience, actually by default it should be calculated with a stiffness factor of 1, which is the normal like situations. You can, if you face like only if you face like convergence problem, you can find this like option in every like contact, especially on the frictional and the frictionless like contact types. You can like adjust the normal stiffness like to 0.1 or 0.2, but you have to know like when you reduce the stiffness factor, the results will not be like accurate as much as when it's like 1, but it will help for sure in some scenario like to get like results at the end and to improve like convergence stability. So like it's allow like a minor mathematically penetration actually, which in some cases, especially when you have like a round face on a flat plate, like for example, it helps like a lot to converge this problem like faster. And like in exchange like for highly stable and successful solution run, of course, like you will lose some accuracy, but you will not get so wrong like results, but it will help to get results at the end. So I hope you get like understand the explanation of each one of these contact types. I'm glad like I'm glad like to give you like more information that I'm planned to do like actually on the next videos about the topic of contacts, more advanced like explanation. And I hope like you did find this video like helpful and informative. So if you found this like video like helpful, like make sure to subscribe and like the video, and I'm gonna see you in the next video.